Alright, so in this section we're going to apply what we know, what we've learned about phase changes or changes in state, and calculations that we've seen in some of the previous chapters. So the first example that we're going to take a look at is what happens when a substance fuses or melts. And we're going to use the term fusion and melting interchangeably. They mean the same thing. Okay, fusion is the same as melting. And when a substance changes state or changes phase, remember the temperature does not change, right? So temperature actually stays constant. The heat that you need to provide to turn 1 gram of a solid into a liquid at its melting point is known as the heat of fusion. All right, so that's the amount of heat energy you need to provide to convert 1 gram of something, of a solid, to a liquid at that melting point. So water is a good example, and for water, in order to melt 1 gram of solid water, which is ice, we need to provide 334 joules of heat to melt that 1 gram of ice. So we can use that heat of fusion as a conversion factor. All right, we can say 334 joules of heat is needed to melt 1 gram of our ice. So we can set up an equality, and then we can turn that into two conversion factors like we've done previously. So let's take a look at an example of this. So down here it says ice bags are used by sports trainers to treat muscle injuries. If 260 grams of ice are placed in an ice bag, how much heat in joules will be absorbed to melt all the ice at 0 degrees Celsius? All right, so let's take a look at that. We're given 260 grams of ice, which is again solid H2O. We need to calculate how much heat will be absorbed. In order to melt that ice. And the heat in that case is going to be provided by your body. Your body loses that heat, which is why it feels cold. So how much heat is needed to melt this ice? That's what we need to find. So what we're going to use is we're going to use the heat of fusion for water, for solid water or ice, which we just saw was 334 joules per every 1 gram of ice. Let me just double check that we have that the right value, 334 joules for every 1 gram of ice. All right, so we start with, we're given our 260 grams of ice. We need to convert that to heat, which has units of joules. So we want our joules on top, 334 joules. And then if that's for every 1 gram of ice, that goes underneath. So the grams of ice cancel, and we just end up multiplying 260 times 334. All right, so if we multiply that, we end up with, let's see down here, we get 8,680 joules as our final answer. All right, and then if we look at our sig figs, we have 3 sig figs here, we have 3 sig figs. So we have 3 sig figs in our final answer. So we've seen we can use the heat of fusion. So again, fusion is going from a solid to a liquid. Right, fusion is just another word for melting. And then when we go from a liquid to a gas, okay, that's called vaporization. So we can use, there's also a heat of vaporization as well for water, for all substances actually, that we can look up in tables to figure out how to do our calculations. So let's take a look at how we can compare and sort of recap some of these terms with what we saw in a couple of the earlier chapters. So from the earlier chapters, we saw that the we can use the heat equation, and the heat was equal to the mass of a substance times the specific heat, which was C, times the change in temperature, delta T. All right, so we were able to use that equation before to calculate the heat either given off or absorbed when a substance changes its temperature. Now we're going to use our new relationships. We can now take the mass of our substance times the heat of fusion or the heat of vaporization in order to complete that calculation. All right, so we've seen, if we look at our table here, we've seen a few of these before. We've looked at the mass times the change in temperature, delta T, times specific heat. We can use that for a solid. When a solid increases or decreases in temperature, we can also use that same relationship for a liquid. We can calculate the heat by multiplying the mass by the change in temperature, by the specific heat. And we can do that for a gas as well, right? So all of these are in the form mass times delta T times C, which is the specific heat. The new thing that we just learned is when a substance is melting, when it's undergoing a phase change, either melting or vaporization, we can calculate the heat involved in that process as well by simply multiplying the mass by now the heat of fusion, if we're looking at fusion or melting, or we can multiply the mass by the heat of vaporization if we're looking at a substance vaporizing. So we can then use all of these relationships, or however many we need, to calculate the total heat that's either absorbed or given off when a substance changes temperature drastically, going from a gas all the way up to a solid, or going in the other direction. So let's take a look at how we can use this information. All right, so here we have an example. It says to calculate the total heat in joules, right? So that's what we need to calculate to convert 15 grams of liquid ethanol at 25 degrees to a gas at its boiling point of 78 degrees Celsius. And we're told that the specific heat of ethanol is 2.46 joules per gram Celsius, and then we're also given the heat of vaporization for liquid ethanol as 841 joules per gram. So we want to think about here what's happening in this problem. All right, so we're given, we have 15 grams of liquid ethanol, and we're also given the starting temperature. So our initial temperature here is 25 degrees Celsius, and we need to heat that up. We're going to heat it up until the final temperature gets to 78 degrees C. And then we're told what the specific heat of ethanol is. So our specific heat C is 2.46 joules per gram degrees Celsius. And then we're also told that the heat of vaporization is 841 joules per gram. All right, so, and then we need to calculate here. We need the total heat in order to do this. So what is actually happening in this when we heat this ethanol up? So we're starting off with our liquid ethanol. So we would chart that on a heating curve. So we have our temperature here and heat that we're providing. So we're going to start off at a certain point. We're going to heat that up, and as we heat it, so we're starting here at 25 degrees. As we heat it, we're going to see that the temperature starts to increase until we get to 78 degrees Celsius, which is the boiling point. And at that point, extra heat that we add doesn't increase the temperature, but it goes into boiling or vaporizing the ethanol. All right, so that's what's happening with our sample. We're starting off down here on liquid state. And then when we get to this point, all right, that's going to be our vaporization. So in this first portion here, the liquid is warming up. So we can calculate the heat needed for that process. All right, so the heat for that step of the curve is the mass times the specific heat times the change in temperature. All right, the mass we were given as 15 grams. We are told that the specific heat C is 2.46 joules per gram degrees Celsius, and our change in temperature is the final minus the initial, so delta T is 78 minus 25, so that's going to give 53 degrees C. So that goes in over here, so we can calculate the heat for that first step in yellow here in our heating curve. Alright, so we stick that in our calculator and we get 1955.7 joules. If you look at our units, the grams and the degrees Celsius cancel away. Alright, so if we look at our sig figs, alright, we have 2 sig figs, 3 sig figs, 2 sig figs. So our final answer should have 2 sig figs. So I'm just going to put a line over those first 2 sig figs so I can keep that in mind. So that's the heat needed for the first part of this curve. Now we also need the heat here for the vaporization because we're also vaporizing it when we get to the boiling point. All right, so the heat for that portion now is equal to the mass times the heat of vaporization. Okay, so the mass we saw was 15 grams. The heat of vaporization is 841 joules per gram. So grams go away. So the heat for this region here in our graph, in pink, all right, we just multiply 15 by 841. Okay, so that's going to give us 12,615 joules for that portion of our graph. So then the total heat would just be the sum of those two. All right, so we're going to add together those two numbers that we calculated. So we have 1955.7 joules, 0.7 plus 12,615 joules. So we add those together. Okay, so that's going to give us 14,570.7 joules. And if we keep track of our sig figs, let's see here, we should have 2 sig figs in each of these. So then our final answer here, we're going to round this to 2, to those first 2, so that'll give us then 15,000 joules as our final amount, or this is the same as 15 kilojoules. Alright, so we can use the relationships we've used before, right? We've seen the heat equation, we've seen this heat equals mc delta T, and that gives us the amount of heat here in yellow, the yellow portion of our graph. And then the new equation that we've learned is the heat that's needed or given off during the phase change or the change in state, and that's on our pink region. In this case it's vaporization, and it's the mass times the heat of vaporization, and we just simply add those together and we end up with our total heat needed for this process.